In this video, I'm going to take you through a review of our trigonometric ratios. So this is our sine, cosine, and tangent ratios when we're dealing with right angle triangles. So I've just placed SOHCAHTOA there just as a reminder of how we know the relationships we use for sine, cos, and tan. So remembering the sine of an angle theta is the opposite side to the hypotenuse. Cosine of an angle is the adjacent side to the hypotenuse, and the tangent ratio of an angle is the opposite side to the adjacent. How we decide which one we're using depends on the angle that we're looking from and the sides involved. So let's look at an example to make this a bit clearer. So in our first triangle, we have a right angle triangle. We know an angle of 34 degrees. So if I'm looking from this angle, I have got the opposite side over here on the left, which I don't know anything about, but I've got the side adjacent, which means next to, and of course the hypotenuse, which is opposite the 90-degree angle. So I've got a situation where I want to find side X, the adjacent side, and I've got the hypotenuse. So I'm looking at the ratio adjacent over hypotenuse. I'm going to use cosine ratio. So the cosine of the 34-degree angle will be equivalent to the ratio of side X over 500. To isolate X, I'm going to undo divide by 500, which means I'm going to times by 500 on each side. And that gives me, when I put this into my calculator, 500 times the cos of 34 degrees is 414.52 meters to 2 decimal places. What we do want to make sure is when we're calculating with trig ratios or sine, cos, and tan, that our angle measure on our calculator is in degrees, not in radians or gradients. That's usually denoted on a scientific calculator at the top by a D or the word DEG, or on our class pad at the bottom by DEG. And if it doesn't say that, just tap the word rad or grad at the bottom of your class pad until it changes to DEG. In our second example here, we've got a right angle triangle with an angle of 35 degrees. Looking from that angle, I've got the side opposite involved and the adjacent side that I want to find. So opposite over adjacent is our tangent ratio. So the tan of 35 degrees is going to be 9.2 over x. Now x here is a denominator. So I don't want it as a denominator, I want it as a numerator. So if I multiply both sides by x, that's going to make sure that the x removes itself as a denominator. So I've got x times tan 35, remembering tan 35 is a value, so I can then divide by tan 35. I am not going to find out the value of tan 35 and use that because I don't want to round at this point. I only want to round at my final answer. So placing this into my calculator, 9.2 divided by the tan of 35 gives me 13.14 meters. Let's take a closer look at this triangle for a moment. I actually know all three angles in this triangle. I've got a 90-degree angle, I've got a 35-degree angle, and so the angle that's left over must be 90, take that 35, which is 55 degrees. And triangles have a really lovely relationship between an angle and the side opposite. So the 35 degrees is opposite 9.2 meters. And then I have the 55 degrees is opposite my side X, which we found is 13.14 meters. I should always notice in a triangle that my smallest angle is opposite my shortest side. So I can therefore know that X being 13.14 meters does make sense because it's opposite a larger angle of 55 degrees. So when you're calculating, always just check that your answer makes sense in the context of the diagram or situation you're looking at. So let's have a look at part C. I've got a right angle triangle. I know two sides, but this time I want to find the size of angle X. So I'm still going to look from that angle, and I recognize that I've got the opposite side involved and the hypotenuse. So I'm going to use the sine ratio. But this time I'm going to solve for angle X. So the sine of x degrees is going to be the opposite side over the hypotenuse. So to undo the function here of sine, I'm going to do the inverse sine. So I'm going to say that x equals, and I'm going to inverse sine that fraction. And we write that as sine with a little -1. I want to make sure that I am inverse sining that whole value of 28 over 50, not just the 28, and then divide 50 so that I don't have an error in my solution. If we pop this in our calculator, x becomes 34.06 degrees to 2 decimal places. So in a moment, I'd like you to pause the video and have a go at the situation in part D. So when we look at this situation, we can identify that we've got a small right triangle, we've got a base length of 15 centimeters and an angle, but we also have a very large right triangle where we have side x opposite the 90-degree angle. And we want to find side x of that large triangle. So, and also want to find y, which is the length denoted by the arrow line, which is the side of a non-right triangle. So in order to find these two, we need to find some other pieces of information first. If we want to think about the small right triangle first, my hint to you is to find side length m and identify what angle n is. So that's going to help you know the angle in the large right triangle. Hopefully that will help you then find another side length after x to find side y. So I want you to pause and spend about 5 minutes having a go at this question and come back and unpause and have a look at a possible solution. So hopefully you started to think about how you can build some more answers in this diagram that's going to help you first find side x. So I'm going to start by finding side m using that small right triangle. So looking from the angle of 64 degrees, I want to find the opposite side m over the adjacent side 15. So the tan of 64 is m over 15, so multiplying by 15, m is going to give me 30.75 centimeters. I also know that angle n is going to be 26 degrees because that is 90, take that 64 degrees in that small right triangle. That's very helpful because this larger angle that I'm going to highlight in green is going to be 56 degrees. So for the large right triangle, that's going to help me find side x. So looking from this angle of 56 degrees, I know side m, which is adjacent, and I know side x, which is the hypotenuse. Well, I want to find it. So I can say the cosine of 56 degrees equals side m over x. And I want to find x, so I'm going to multiply by x and divide by the cos of 56. And you'll notice that I'm not putting in the value 30.75 because I don't want to use a rounded solution. And that's the beauty of a class pad, that you can copy and paste or highlight and drag down that whole value so you won't lose accuracy. So when I say m divided by cos 56, it gives me x as 54.998 centimeters. So I'm going to say x is 55.0 centimeters. So now I've got the situation of finding length y. The problem with length y is it's not part of any right triangle. So our only other option is to find length, what I'm going to call p. P being the whole base length of this right triangle. If I can find P using a ratio, trigonometry ratio, or Pythagoras, then I can subtract 15 to find Y. So I'm going to find P using Pythagoras. So it's the square root of the hypotenuse, which is x squared. Take the other side, m squared. So if I'm going to do that, I'm going to get P as 45.6 centimeters, 0.60 centimeters. So from there, I can find Y, because Y will be exactly 15 centimeters shorter. So Y is going to be 30.60 centimeters to 2 decimal places. So here, let's have a look at a question in a context. We've got a glider plane being towed behind a vehicle. It's released from the tow rope at a height of 85 centimeters. So before we move on, I'm going to draw a picture of that. We've got a car moving, or a vehicle moving along. And so let's just say car. And a glider plane is joined to the car by a tow rope. So I'm going to put P for plane. It is at a height of 85 centimeters. So that's a vertical height of 85 meters. At the time that the glider plane is released from the car, the rope makes an angle of 40 degrees with the vertical. So highlighting in yellow is the tow rope, highlighting in green is the vertical, and so that angle of 40 degrees is between the tow rope and the vertical. So we can build a picture based on this, and we notice that it is a right triangle. We want to know how long is the towing rope to the nearest centimetre. So I'm going to put a little R here for rope, and we're going to find that to the nearest centimetre. So let's take a look. Looking from an angle, because I've got a triangle here, I know the adjacent side and I want to find the hypotenuse. So I'm going to use the cosine ratio. So the cos of 40 degrees is equal to 85 over R. So R is going to be 85 divided by the cos of 40. So when we pop this into our calculator, we get R as a value of 110.9596 meters. Okay, but we want it to the nearest centimetre. So R is going to be multiplied by 100 to get it to centimetres. So that's going to be 110 times 100. So 95.96 centimetres. So we can say the rope is 11,096 centimetres long, and that is to the nearest. So now I'd like you to pause the video and have a go at question 3. It's in a context, so read the question, form a diagram that you label to think about how you're going to find the length of the new ramp. So hopefully you began with a picture of a ramp. The ramp itself in green is 2 meters long with an angle of 40 degrees to the floor. So I've just hashed in red where the truck is and placed the line where the new ramp needs to be with an angle that's only 20 degrees. So what we want to find out is what is the length of this new ramp. So I'm going to call that length X. Okay. So when we have a look at the information we've got here, I want to essentially find that value of X using a right triangle and an angle of 20 degrees. When I look from that angle, I can identify I want to find the hypotenuse, but unfortunately I don't know another side. So first of all, I need to find another length. And the length I can find is in blue, light blue, and I'm going to call that side Y. So first of all, if I look from the angle in the larger or original ramp, I've got the adjacent and the original ramp as the hypotenuse. So the cos of 40 degrees equals Y over 2. So Y is going to be 2 lots of the cos of 40, which is 1.532 meters. It makes sense that Y is less than 2 meters because 2 meters ramp is the hypotenuse in our triangle. So this means we can now find x. So looking from an angle of 20, we're going to use the cosine ratio. We've got the adjacent side y, which we know over the hypotenuse x. So x is going to be that y value we've just found using the whole value in our calculator, not a rounded value, dividing that by the cos of 20, and we get 1.63 meters. So we're going to say that the new ramp is 1.63 meters long. Now this makes sense that it should be less than 2 meters because the angle is reduced, which means the length of that ramp will be reduced.